When you hear the term electricity markets, forget the stock tickers and the traders yelling on a floor. We're not really talking about just money here. We're talking about the invisible, complex operating system that keeps our lights on every single second of the day. And today, we're going to explore why this operating system isn't just a nice-to-have, it's the only thing standing between our modern world and a total blackout.
Okay, so let's start with what is just a wild concept. Electricity is pretty much the only product in the world that has to be created at the exact, precise instant you decide to use it. The moment you flip a light switch, somewhere, a power plant has to spin up its output to match. So with millions of us making these decisions constantly, the big question is, how on earth does the entire grid not just collapse every single day?
Well, the answer lies in a system that was specifically designed to solve a set of what seemed like impossible problems. So first, let's break down the 4 big challenges that make electricity a commodity that's truly unlike anything else.
First up is this idea of instantaneous balance. Supply has to equal demand, not roughly, not on average, but precisely, every single second. There is no buffer, there's no inventory you can draw from. If we're off by even a tiny fraction, the whole system can become unstable. It is a constant, high-stakes tightrope walk.
Now this next one is really interesting because it gets to a core misunderstanding. You simply can't tell an electron which wire to take. Unlike, say, gas in a pipeline, electricity flows across every single available path at the same time, always following the path of least resistance. This means you can't just sign a piece of paper to send power from point A to point B. Physics and the grid itself are what actually decide where that power goes.
And you know, those paths for electricity, they're not infinite superhighways. The grid is a physical network. It's made of wires that have very real, hard limits. And just like highways, they can get totally jammed up. If you try to push too much power through one line, it can overheat and fail, creating these bottlenecks that can cut off entire regions.
And finally, to manage all this chaos, the grid needs a backup plan, constantly. Power plants can fail without warning, demand can suddenly spike on a hot day, so the system has to keep a whole fleet of other generators just spinning in reserve, ready to jump in at a moment's notice. So you combine all 4 of these challenges, right, and it becomes pretty clear that no single person, no central planner, could possibly manage all this complexity in real time.
So, if a central planner can't possibly do it, what can? Well, this brings us to the market's really elegant solution. It's a system designed to use the pretty simple logic of economics to coordinate the immense physical chaos of the grid.
And the principle at the heart of it all is called the merit order. It's a beautifully simple idea. You always use the cheapest available electricity first. That's it. This one rule helps make sure the system runs as efficiently and as cheaply as possible, at all times.
So let's just walk through how this actually works. First, every single power plant out there, from a huge solar farm to a small gas plant, bids a price into the market. This is basically their cost to produce just one more unit of power. Step 2, the grid operator takes all these bids and stacks them up, from the cheapest to the most expensive. So you get wind and solar at the very bottom with a cost of pretty much 0, then maybe nuclear, then coal, and finally the most expensive gas plants at the top. And then, and this is the most important part, the operator starts dispatching these plants one by one, going up the stack until demand is totally met. And the price of that very last power plant they needed to turn on? That price becomes the market price that everybody who generated power gets paid.
But, of course, there's a twist. This simple, elegant economic model runs headfirst into a very messy physical reality. And this brings us to what we can call the grid's traffic jam problem.
Okay, so here's the official technical definition. Congestion happens when the cheapest way to make electricity, according to that merit order we just talked about, just isn't physically possible because the wires in that part of the grid can't handle all that power.
But honestly, the best way to think about it is this. There is a literal traffic jam on the electron highway. The cheapest power plant is way over on one side of the state, but the big city that needs all the power is on the other side, and the transmission lines in between are already totally full. You can't squeeze any more electrons through.
And this creates what is probably the single most important question in designing an electricity market. If the physical location of power is just as important as how much it costs to make, how in the world are you supposed to price it? How do you account for these traffic jams in the price itself?
And that one question leads to 2 fundamentally different philosophies, 2 competing ways of thinking about how to manage all this congestion on the grid.
So on one side, you have what's called zonal pricing. It's simple. You just divide the grid into a few very large areas or zones and set one single price for that whole area. It basically ignores all the little traffic jams inside the zone. On the other side, you have nodal pricing. This is way more precise. It calculates a unique price for thousands of different individual points, or nodes, all across the grid. It fully respects the laws of physics.
So let's look at this comparison a bit closer. Zonal pricing, super simple, just a handful of price areas. But because it ignores all that internal congestion, the grid operator has to come in after the market runs and manually fix all the problems. This is a really costly process called redispatch. Nodal pricing, on the other hand, with its thousands of price points, it prices that congestion directly into the market from the start. And here's the really crucial point. Because of that, it creates these incredibly strong and precise signals about exactly where the grid needs a new power plant or a new transmission line, which ultimately leads to the highest possible economic efficiency.
So I know, this is all pretty technical, but why does this design choice matter so much? Well, because as we're about to see, the choice between ignoring physics or embracing it, it has multi-billion-dollar consequences for everybody. So let's dig into this redispatch problem you find in zonal markets. So the market runs, it finds the cheapest power available. But then the grid operator looks at the result and realizes, uh-oh, we physically can't get that cheap power to where it needs to go. So they have to get on the phone and manually pay a more expensive local plant to turn on, and then pay that original cheap plant to turn off. It's a messy, inefficient, and very, very expensive patch.
And just how expensive is it? Let's put a real number on this. In Germany, which uses a zonal market, the annual cost of just this redispatch, this cost for the manual fix because the market decided to ignore the physics of the grid, is approximately 4.2 billion euros every single year. That's the price tag for having a market design that isn't lined up with physical reality.
And this brings us right to our key takeaway. Nodal pricing, by seamlessly integrating physics and economics, really does act as the grid's modern operating system. It is the only design that can scalably and efficiently handle the growing complexity of the future grid, a grid that's going to be full of intermittent renewables, millions of electric vehicles, and huge batteries. It's not just a market, it's an optimization engine for reality.
And that leaves us with one final big question for the future. We know nodal pricing is the state-of-the-art operating system for today's grid, but as millions of new solar panels and electric vehicles all connect, adding so much more complexity and variability, what does version 2.0 of this system even look like? What's the next critical upgrade for the grid's OS?